Good morning to this 19th lecture of the course Compressible Flow and Gas Dynamics. Okay, so in the previous lecture we have discussed about the shock waves, particularly oblique shock waves and reflections of the shock waves, and we did some numerical problems related to that. Okay, today we will start our discussion on interactions of the shock waves. So for understanding that particular topic, we need to know about one more tool, which is particularly known as pressure deflection diagram. Okay, so pressure deflection diagram is really important in terms of analyzing the interactions of different shock waves. Okay, so basically if we see, you will be remembering in the previous case, we have seen actually two kinds of shock waves. So first we have seen that if we have some deflection over here, then a shock wave will form something like this. Okay, so this is one shock wave, and when this shock wave is touching this boundary, then actually it is deflecting in this downward direction. So we are having a reflected shock wave also. So this we called incident shock wave, and this we called as nothing but the reflected shock wave. Okay, but interestingly, what was happening when a streamline was entering at this point, so this was getting deflected like this. Okay, and then this streamline was getting deflected like this. So this also we have seen how a streamline actually deflects through these two shock waves. Okay, so one interesting point you will be finding over here, that one shock wave actually I am getting over here, which is placed something like this. Okay, so if you see your incident shock wave, so that is having orientation something like this. Okay, and in this shock wave what is happening basically, if this is your start point, so exit point is something like this, and this is deflecting at an angle theta. Now if you see the other shock wave, there what is happening, if you consider your reflected shock wave, so its orientation is something like this. Here streamline looks something like this. Sorry, so say if I consider that it is coming at certain angle, okay, it can come straight also. So if it is coming straight, if I particularly not take the situation, if I take these two as nothing but the separate identities. Okay, so if a streamline is coming like this will deflect something like this. Okay, and here I will be having this angle as theta. So one important observation we can make from here is that whenever we are having a shock wave and streamline actually interacts with it, the bending of streamline always takes place towards the shock wave. So here you can see this is the direction which is towards the shock wave. So streamline has actually bent towards the shock wave. It has not gone away from the shock wave. So it means always flow streamline tends to bend towards the shock wave. Similar case you can see over here. So when I am entering a straight streamline, it is actually moving towards the shock wave. Fine, it is not moving away from the shock wave. Okay, that is one interesting point. Another important point you can see is that here in first case when deflection is taking place, this deflection angle is oriented in counterclockwise direction. So I can say that this deflection angle is in the positive direction. Okay, and here if I talk about this particular deflection angle, this is in clockwise direction, and I can say it is nothing but the negative deflection. Is this point clear? So in one case we have positive deflection, in another case we have negative deflection. Now it is interesting to note that this type of shock wave which results in positive deflection is particularly called as left running shock wave. Okay, and the family of shock waves which results in negative deflection, particularly we call these as nothing but the right running shock waves. Is this point clear? So one family we have called as nothing but the left running shock waves. Okay, and another family we have called as the right running shock wave. Okay, so now let's try to see if we have a left running shock wave, then basically how our pressure deflection diagram will look for that. Okay, so let me now construct a pressure axis, and this side I will construct a theta axis. Okay, now let's consider that my initial pressure is P1 when streamline is coming like this. So if streamline is coming in the upstream direction parallel to this horizontal line, so I don't have any deflection angle, so it is aligned actually. Okay, so because with reference to this direction it is at zero orientation, so corresponding to zero angle I can say this is my point number 1 having pressure P1. Okay, now if you are having theta angle, then behind the shock wave what will happen? We know that behind the shock wave always pressure increases. P2 is always greater than P1. Is this point clear? So I can say that if I have any angle theta, then corresponding to that angle theta, say this is my point 2 over here. Okay, this is corresponding to some angle theta, I can say this is my point 2. However, if I take a number of points between this point 1 and 2 for different values of flow deflection, what will happen? Say if I have very small angle theta 1, then I will get some point like this as my output point. If I have angle theta 2, then this will be output point. If I have angle theta 3, then this will be output point. So like this I can have a number of points over here. Okay, and this pressure will keep on increasing up to the value of theta max. So from where I am taking this conclusion, if you see our theta beta m diagram, how it looks, something like this. So corresponding to this situation, what we have a very weak wave, okay, which will not change the pressure, so like a Mach wave. So you can see this exit and entry point will be the same. If you increase the angle, slowly strength of the wave is increasing, so it means it is increasing the value of pressure in the downstream. Then I reach a situation of theta max. At theta max our pressure will be some higher value. Then if I once again decrease the theta, but now in the direction of strong shock wave, so strength of the shock wave keep on increasing more, but this portion is more steeper, so here number of points will be very less, okay, for the same value of theta. And then finally I will be getting nothing but a normal shock wave. So say if I keep on increasing the value till my which point is achieved? Theta max. So say this is my point theta max. Okay, so what I am doing actually, I am saying that if I have wave at different deflection angles, then what will happen? So I will get so inlet point is same, that is corresponding to Mach number 1 only, but this output for the same Mach number is actually output pressure is basically changing, inlet pressure is the same. Okay, so I will get this point like this, and then after this point what will happen, because this here we are having a more steeper portion and further angle has started decreasing, so pressure will keep on slightly increasing. Okay, pressure will keep on increasing, and finally corresponding to the case of a normal shock wave, pressure will be highest. Is this point clear? Now if I draw the locus of all these points, I will get a curve. So what I am doing now, I am drawing the locus of all these points. So are you able to get this type of curve? Okay, so this is nothing but my pressure deflection diagram which is covering the entire range of shock waves starting from very weak Mach wave to the normal shock wave. Okay, so in this entire range from 0 to theta max, particularly for the weak shock wave region, this will happen, and for strong shock wave region from this point beyond theta max, we will get this type of variation. Okay, and this particular curve is nothing but for a Mach number of m1. Okay, upstream Mach number for this entire curve was m1. Okay, so this type of diagram is called as pressure deflection diagram, where what I am taking, I am fixing my inlet pressure condition, and then I am varying actually different deflection angles to see the exit pressure points. Okay, this particular pressure deflection diagram is, this right portion is actually applicable for a left running wave. Why left running shock wave? Because for that theta will be positive. Okay, so if this is 0, so in this direction theta is positive and in this direction theta is negative. If I have to consider a right running shock wave of the same strength, same case, same Mach number, so then that will be nothing but a mirror image of this. Maybe I may not be able to draw exactly correct, but you have to understand that this is nothing but a mirror image of first one. Okay, so this is my complete pressure deflection diagram, but this side is for actually a right running shock wave. So this entire diagram is for my Mach number equal to m1. If I take any other Mach number m2, then what will happen? My point will start at the same location, but if m2 is less, then curve will take actually it will have less value of theta max, because you have seen that this is for m1. If I take some value of m2 which is lesser than this, then theta max will decrease. So for any value m2, if I start at the same point, P1 pressure is same but m2 is less than m1, then I will get a diagram something like this. So this is for m2 which is less than m1. Is this point clear? So this important diagram is called as nothing but the pressure deflection diagram. Okay, and this pressure deflection diagram, P theta diagram, can be used while analyzing the interactions of the shock waves. Okay, so let's consider the case which I have shown you in the previous page. If I take that particular case, and for that if I try to draw the pressure deflection diagram, say this is my angle theta, so what will happen over here? First I will be having a shock wave something like this, incident shock wave, then I will have a reflected shock wave something like this. Okay, so if this is my region 1, this is region 2, this is region 3, so I will find that if I have a streamline something like this, it will bend say at an angle of theta 1, then it will bend here something like this. Okay, so this angle, if you see, this is my angle theta 2. Is this point clear? And here Mach number will be m1, here Mach number will be m2, and here Mach number will be m3. Okay, now let's try to construct the pressure deflection diagrams for this situation, and let's understand how basically I can represent this entire process of 1, 2 to 3 on pressure deflection diagram. Okay, theta p. So if you see first case, I am starting at point 1, this is my point 1, and my Mach number is m1. So say corresponding to M1, my curve is something like this. This is pressure deflection diagram for M1. Okay. Now what happened? Uh, when I moved from point 1 to 2, my flow has deflected through plus theta 1. Okay. So say this is my angle over here as nothing but plus theta 1. So this will be the pressure at point 2. Is this point clear? And this is my process 1 to 2. Is this point clear? Now, if you see this 2, which is already at an angle theta 1, this is now becoming the incident streamline for this reflected shock wave. Okay, so as it is becoming upstream streamline, so now our angle will be measured with reference to this particular line. Okay, or in another sense I can say that this point 2, which is at an angle theta 1, now this will act as nothing but the starting point for this second wave. This will be my starting point. So it means my pressure deflection diagram will now start from point number 2. Okay, and this pressure deflection diagram will be for Mach number M2, which is less than M1. So now overall origin of my diagram will be less. Is this point clear? So from point 2, I will make another pressure deflection diagram. First I am drawing the complete one. Now let's see what will happen. Okay, so now I am drawing actually the entire one. Okay, is this clear? So this is for entire M2, which is less than M1. So vertex of this pressure deflection diagram has actually shifted. Now you are correct. If you see this second wave, so it was in this direction. So this we have already accounted because we have started its pressure deflection diagram from different vertex, which is starting at theta 1. So now with reference to this, it is actually making an angle of theta 2, and this theta 2 is in the negative direction, and this is a right running wave. So here I am seeing the negative deflection. Okay, so it means that from this point 2 now I have to move in the direction of decreasing theta. So decreasing theta is this direction, and in the direction of decreasing theta I have to move till my angle of deflection is becoming from this point I have to move theta 2. Okay, starting from this point I have to move back theta 2. So if I move back theta 2, you can see over here, if this angle is theta 1, this angle is theta 2, because these two lines are parallel. So in this situation theta 1 is equal to theta 2 is equal to theta. So it means my, if I move theta 2 in the backward direction, I will reach at this point. Okay, once again my flow has become over here horizontal. That also you can see. Okay, so this is my point number 3, and this is the process 2 to 3 over. Okay, so you can clearly represent a process nothing but on a pressure deflection diagram. Okay, so I am starting at point 1, then going at 2, and then entering once again at 3. Okay, now let's try to see up to this point. Is it clear? So how I have constructed this p theta diagram for this one? So this is very actually easy to understand. Okay, now let's try to see interaction of shock waves of opposite family families. So if I have opposite family shock waves, then how these will actually intersect? So in this case we have seen a shock wave which is incident and one is reflected. Now I will consider that I have two shock waves starting at the two shock waves which are incident only but are of two opposite families. How these interact actually? Okay. So interaction of shock waves of two different families. Okay. So let's consider a situation that I have a surface and it is having some compression corner at an angle theta 2. Okay. So this surface is having compression corner at an angle theta 2. I have another surface which is having compression corner at an angle theta 1. Okay. And such that theta 1 is greater than theta 2. This is the situation. Okay. So now what I will see, I will see a shock wave which will start from this point. Say this is my shock wave which is starting at this point and say making angle beta. So this shock wave I can say nothing but a left running shock wave. Similarly, another shock wave will start from this point and if you see this shock wave is nothing but a right running shock wave and say both are interacting and meeting this point. Okay. So this is my point A, this is point B, and let's consider both of these are meeting at point C. Now after this point what will happen? Till now we have talked about the shock reflections. Now we will be having shock refraction. Okay, so you know the difference between reflection and refraction. Okay, so now let's consider that this wave which has come as BC, this has reflected something like this, refracted something like this. So this is my one refraction and this AC has refracted something like this. So this is my wave CD and this is wave CE. So what I am saying that refraction of B to C is C to E and refraction of A to C is C to D. Is this one clear? Okay, interesting. Now let's see what is happening. This is my region number 1. If you see upstream condition will remain same over here. Say this is my region number 2. This is region number 3. Then behind this one region number and behind this one region number 5. Is this one clear? Because whenever you will see a flow is interacting with a wave, it will change. So that's why we will be having multiple regions over here. Okay, so let's try to see a streamline which is coming and striking this point. Here another streamline which is coming and striking this point. So what will happen here? This will bend toward like this. Okay. And its angle will be how much? Its deflection angle will be theta 2. This will bend something like this and its deflection angle is theta 1. Okay, so one has deflected at an angle theta 2, other has deflected at an angle theta 1. What will happen after this point? Once again this will deflect. Say it has deflected and taken this direction, and angle between this and this angle is my theta 4, sorry, theta 3. I have not taken yet theta 3, na? This angle is my theta 3. Similarly, this is there, it will deflect towards this side, and say this angle is theta 4. Is this point clear? So you have to follow the line. Okay, this first has deflected at an angle theta 2, then it has struck with shock wave, refracted shock wave CD, and then deflected at an angle theta 3. This has first deflected at an angle theta 1, then struck with CE and deflected at an angle theta 4. Okay, is this point clear? Now, one important point is that I have taken theta 1 different than theta 2. So, my conditions in regime 2 and regime 3 will be different. Is this point clear? So, it means that my M2 and M3 will not be same. Okay. So, let's now try to construct the diagram first. So, what will happen first? Let me take P theta, this is P, this is theta. Okay, so say this is my starting point 1. So for starting point 1, this will be my, say, pressure deflection diagram for Mach number of 1. Okay, for Mach number of 1, this is my pressure deflection diagram, and this is theta max, and say this is my M1 over here. Now if you see, first we have nothing but this is a left running wave, okay, and this is deflecting through angle theta 1. So I will have a process over here up to angle theta 1, and this will be my point 3. Fine. Then I will have a right running wave up to angle theta 2. So from here I will go back, but I will go, in comparison to this, I will go less distance because theta 2 is less than theta. So it should be below 0.3, but I may have some difficulty in drawing. Okay, consider that this is below point. So this is my point number 2. Is this point clear? Now at point 3 and point 2, I will be having vertex for next pressure deflection diagrams, because if you see here, this point 3 is becoming upstream point for wave CE, and point 2 is becoming upstream for wave CD. Okay, so now I will have nothing but the 2 more pressure deflection diagrams. One will start at point 3, which will be corresponding to Mach number 3. So if theta 1 is greater than theta 2, my wave AC will have more strength than BC. Okay, if this is having more strength, then my M3 will be less in comparison to M2. Is this point clear? So my M3 circle will be smaller and M2 circle will be little bit larger. Is this point clear? So this is point 3. So from here M3 circle I will start. This is my M3 circle. M3 not circle, M3 pressure deflection diagram, M3 P theta diagram. Okay, so one more P theta diagram I will construct at point 2, and this will be slightly larger than the M2, sorry, M3. So this is for M2. Now if you see what is happening, this point 3 is finding a deflection angle towards theta 4, which is slightly bent in the which direction? Theta 4. This is the direction and this is the direction. Okay, so this is in anti-clockwise direction. So theta 4 you have to move from point 3, you have to move, is it anti-clock or clock? Let me amplify this. So this is this streamline, and then this is, and this is angle theta 4. Direction is, so it means from point 3 it has to start along this direction. Fine. And then from point 2, if you see, it has deflected like this. So this angle is in positive side. So I have to move theta 3 distance. How much distance from this point? Theta 3 distance in this positive side. Okay. So from this point I have to move theta 4 distance. So I will be finding that both of these actually will meet at a common point. So if you travel from here theta 3 distance, and if you travel from here theta 4 distance, you will find this as nothing but your common point. Okay, and this particular common point will designate the states behind this shock wave and this shock wave. So it means it is designating my state 4 and state 5. So what I am saying is that after these two reflections, both of these waves are actually going at single angle of, say this angle is 5. Okay, so these streamlines will be nothing but parallel. So this is my point 4 and this is also point 5. Okay, so corresponding to this, whatever angle I am having, I can say my this angle is nothing but 5. This angle is 5, and you have just now understood that from this point I had to travel how much distance? Theta 4 distance in order to reach this point. So I can make a relation over here that theta 4 is equal to 5 minus theta 2, and from this point I had to travel a distance of theta 3, sorry, yeah, sorry, उससे थीटा 3 किया था ना, हाँ, पॉजिटिव डायरेक्शन, इन पॉजिटिव डायरेक्शन दिस वाज एक्चुअली थीटा 3, sorry. So from this point I had to travel distance theta 3, so this will become my 5 minus, sorry, theta 3 will become 5 minus theta 2, and here I have to travel a distance of theta 4, so my theta 4 will become theta 1 minus 5. Is this point clear? Because from this point to reach this point I had to travel a distance of theta 3, so that is why I can call it as 5 minus theta 2, and here from this point I am traveling a distance of theta 4 to reach this point, so I am calling it as theta 1 minus 5. Now these two relations you can verify from geometry. You have geometrical picture also. So you see this theta 4 1, say let's try to construct this bottom one. So in case of bottom one, what we have? We have a streamline something like this, okay, which is already at an angle of theta 1 with horizontal. Then I have got a deflected streamline, okay, and this angle between these two is theta 4, and then if you see with horizontal, this angle is phi, okay. So clearly you can say that theta 1 will be equal to phi plus theta 4, and from here theta 4 will become theta 1 minus phi. Are you getting geometrically this relation? And you see this one, theta 4 is equal to theta 1 minus phi. So whatever I have driven on this diagram, same conclusion actually I can also make from the geometry. But from geometry, how I cannot make, because this geometry I don't know in exact orientation what will happen. Okay, so basically from p theta diagram I can make this conclusion. Fine. Now now interestingly, one point is there. From point 1 to point 2, this Mach number is different. From point 1 to 3, this Mach number is different. Moreover, beyond point 2 to 4 also, we have a different shock wave. Here we have a different shock wave, and upstream Mach numbers and angles are also different. So, there are high chances that the conditions in this particular region, like region 4, will not be exactly equal to the conditions in region 5. So we will be having some discontinuity between region 4 and region 5. That particular discontinuity I can represent with the help of a line over here. Say this is a dashed line, I am drawing it actually, and this should also have angle phi, because these streamlines are parallel. So below this, in the streamlines below this dashed line, there are different properties, and above this there are different properties. So that's why this particular dashed line, which is an angle phi, this is the line which demarcates the difference of properties between the two layers, okay, and this particular line is called as slip line. Now there are two important conclusions. First is that just above and below the slip line, our pressure should be same. Okay, so it means that the necessary condition for a straight slip line to occur is that P4 should be equal to P5. Why? If any pressure is larger, then that will not able to result in a straight slip line. We will be having a curved slip line. Whereas over here we are referring to our flow conditions as nothing but the 1D or 2D flow conditions, where our streamlines are nothing but straight, parallel. We are not talking about the curved boundaries which or curved streamlines which particularly occur in case of three-dimensional shock waves. Is this one clear? Because we want this slip line, this discontinuity to be nothing but a straight line, and this will be a straight line if and only if my P4 is equal to P5. Up to this point, is it clear? Then another interesting fact is that both of these lines should have velocities in same directions. Like region 4 and region 5 should have, this is I am marking as star, so space is not much, but these are important points. Velocities in regions 4 and 5. It means both the regions across the slip line should be in same direction. If I consider that one velocity is like this, other velocity is like this, we are not considering any friction. Okay, we are not considering any relative motion between the two. So physically we will get a situation that one layer without friction moving in this direction is not. Here for a fluid layer it will not be possible if I assume a 1D average velocity for the complete set of layers. Okay, so that way another important condition which should exist for the which should exist for this particular reason is that velocities should be in the same direction, and ultimately this will lead to the situation that both these streamlines should deflect at same angle. Okay, so that is the reason this streamline and this streamline, these are actually parallel, and then slip line is also parallel to this reason. So are these conditions clear? So this is what we can see, that if we are having shock waves of two incident shock waves of different families, then we will find a refracted shock waves, and then how these refracted shock waves will lead to changes in the flow directions and flow properties. Okay, so the necessary condition is that always we will be having the presence of a slip line which will represent discontinuity in some properties. Why in some properties? Because you will find that if strength of these two waves are different, then ultimately what will happen? Mach numbers in the downstream will be different. Entropy change across these shock waves will be different. Okay, because entropy is also one of the important parameter. If and entropy we have seen for a normal shock wave, it's nothing but solely the function of a total stagnation pressure. Okay, so stagnation pressure will be different. Okay, is this point clear? So that's the reason that for this situation to occur, we should have actually same angle and the same pressure. Okay. And in other properties there will be obviously discontinuity, but in these two parameters, pressure and angle, discontinuity will not be there. Okay, so that is why this slip line represent discontinuity in some set of properties, not in all. For example, in pressure it is not leading to discontinuity. Is this point clear? Now next we have nothing but the interaction of same family shocks. If we have two shock waves of same family, then how these are interacting. Okay, to understand this point, we will first need to understand few more things. So let's consider that this is the compression corner having angle theta, and on this compression corner, say I have 3 points. One is point A, one is point B, and another is point C. Okay, so first thing is that in this compression corner I will have formation of a shock wave. So this is my oblique shock wave, and this is a left running shock wave. Okay, say this is making an angle of beta. Now let me consider that from point A I have nothing but a Mach wave. From point 1 I have a Mach wave, and this Mach wave is having angle mu1. Okay, why I am considering a Mach wave? Because we know that in the upstream and downstream of Mach wave there will not be any change in property, and there will not be any deflection in flow. Okay, so I can reasonably assume nothing but a Mach wave over here. So I have considered that I have a Mach wave at an angle mu1. Similarly, from point C also I consider that I have nothing but a Mach wave which is having angle mu2. Why I am considering this Mach wave? Because this will form the basis that can two shock waves of same family can intersect or not. So this basis basically will be found by the Mach waves depending upon the angle. Because if say I am considering that my Mach wave angle is larger than beta, then these both waves will not meet till infinity. If this angle is mu2 is less than beta, then these two waves will not meet till infinity. So with these will not have interactions. So whatever the basis we will be forming for Mach wave, that will be applicable for shock wave also, because for shock wave angle will be always greater than Mach. So here if, okay, so let's try to see what will happen first. So first if I see, I can, if my V1 is velocity in upstream, so this V1 velocity will interact with this. So I can make one point that sine beta equal to Vn1 normal component of this velocity divided by v1. Okay, and for this Mach wave I can write sine of mu1 equal to speed of sound a1 by, what is mu? Sine inverse 1 by Mach number, and 1 by Mach number will be a1 by v1. Okay, now first important point is that we are considering that we are having presence of a shock wave over here. So shock wave will only form if my v1 velocity is greater than speed of sound, because shock wave will form only for a supersonic flow situation. Okay, so v1 has to be greater than a1. So it means that if v1 is v1 or vn1 normal component of velocity has to be greater than actually a1, then only my shock wave will form. Okay, because ultimately what happens, v1 is coming like this, but when we do analysis across the shock wave, it is the normal component which is responsible. The tangential component remains preserved. Okay, so tangential component across a shock wave always remains preserved. So my vn1 in this region has to be greater than a1 for the occurrence of a shock wave over here. Okay, so for a supersonic condition, as vn1 should be greater than a1, that's why I will be finding that this vn1 will be larger than a1. So this will give me the vn1 by v1 magnitude larger than a1 by v1 magnitude. If this magnitude is larger, I can easily say that angle beta will be greater than angle mu1. Okay, so if I have beta angle larger and mu angle smaller, then ultimately if a Mach wave is starting at this point, it has to interact with this particular shock wave. Okay, is this one clear? Now I will stop at this point. So what you can do, you can make the same physical inference for this downstream also. Okay, so for downstream you will be having velocity as v2, and from this velocity v2 you try to check if what will be the relationship between mu2 and beta, which one will be larger, which one will be smaller, and then we will discuss about this topic in the next lecture.